everyone, this is our final poster presentation for CS230. I'm Hao Tiandu and this is my partner Zhuoran.
Hi, this is Zhuoran.
We both come from Department of Chemistry. Our project title is Deblurring Near-Infrared Fluorescence Images with CycleGAN. First, let's start from some introduction about fluorescence imaging. In vivo imaging is an emerging technique to profile the internal status of biological systems. Among different in vivo imaging modalities, fluorescence imaging provides benefits of real-time acquisition with high spatial resolution. However, compared with other imaging techniques like MRI or CT, fluorescence imaging is not that popular in clinical application, mainly because its imaging depth and spatial resolution is limited by scattering, absorption, and tissue autofluorescence. A possible solution for this is to extend imaging wavelengths to a long wavelength window, which is what we defined as the second near-infrared window and NIR2 as abbreviation here. Compared with the visible and traditional near-infrared window, and we define traditional near-infrared window as NIR1 here, fluorescence imaging in the NIR2 window shows advances of improved penetration depth and higher spatial resolution, mainly because of reduced tissue scattering and autofluorescence, and it's shown in the figure A and B here. And recent research, which both of us have been working on, have further extended the imaging wavelengths to the long end of NIR2 window. And that is what we define as NIR2B here. However, even though NIR2B imaging shows unprecedented image quality, fluorescence probes using here always involves heavy metal elements, and they always suffer from biocompatibility or safety concern. Some NIR1 imaging probes have been approved by FDA, but none of the NIR2B probes has got approved yet. So we come up with this idea to train a CycleGAN for transforming NIR2 images to NIR2B images. And here comes of our data collection. Here are some examples of NIR1 and NIR2B images collected in lab. And for data collection, all of the images are collected in Professor Hongjie Dai's lab using an in-gas camera and using our homemade imaging setup. We collected 693 NIR1 images and 867 NIR2B images in total, and those images are unpaired, so this is why we need a CycleGAN. For data pre-processing, the raw data were 16-bit grayscale images with a resolution of 640 by 512 pixels, and images were rescaled to 256 by 256 pixels to reduce training time. And the intensity of the images were normalized to range -1 to 1 to help training. And for our baseline model, neural cell transfer, the images were transformed into a 3-channel RGB image. And for our training test set split, because our dataset is relatively small, we split it into approximately 80% to 20% ratio for training and validation set.
Now let's talk about the method we used. So the baseline model we used is neural style transfer. So we used a NIR1 image as the content image and a NIR2B image as the style image. The content image, style image, and the target image were used as inputs for this pre-trained VGG19 network to calculate the style loss, content loss, and the total loss. So the activations of the content image and the generated image were used to calculate the content loss, which is a mean square error loss. And the gram matrices of the style image and the generated image were used to calculate the style loss, which is also a mean square error loss. It should be noted that the results of these 5 convolution layers were used to calculate the style loss, while the result of this single convolutional layer was used to calculate the content loss. And finally, the total loss is a weighted sum of the style loss and the content loss with hyperparameters alpha and beta, We just choose alpha to be 10 and beta to be 40 in our experiments, and we didn't tune this hyperparameter. We used an Adam optimizer to minimize the total loss with respect to the generated image, so we can get a near IR2B styled near IR1 image as our final output. So another model we use is called CycleGAN. So CycleGAN is a image-to-image translation algorithm using a paired dataset. Here's how it works. There are two generators, GA and GB, and two discriminators, DA and DB. First, we use a real near IR1 image as the input for the generator GA to generate a fake near IR2B image. And the discriminator DB is here to tell whether a near IR2B image is real or fake. So for generator GA and discriminator DB, we can define a adversarial loss, which is just as similar to the adversarial loss of the vanilla GAN. And one thing that we should note here is that the adversarial loss used here is a mean square error loss instead of a binary cross entropy loss. According to the authors of the original CycleGAN paper, they mentioned that the MSE loss is just more stable than the binary cross entropy loss. So we just use their idea here. And similarly, the generator GB can be used to translate a image in the near IR2B domain to an image in the near IR1 domain. And discriminator DA is here to tell whether a near IR1 image is real or fake. And similarly, we can define another adversarial loss for GB and DA. However, the thing is that the adversarial losses here are not enough to guarantee the translation is meaningful. For example, let's think about an extreme case in which all the near IR1 images were transformed to the same near IR2B image. So the result is not meaningful at all, but we can still get a very low adversarial loss for the generators. To avoid this from happening, we introduce something called cycle consistency loss. Here's how it works. For the generated near IR2B image, it can be transformed back to the near IR1 image by using the generator GB. And if GA and GB are trained perfectly, the reconstructed near IR1 image should be exactly the same as the original near IR1 image. And similarly, the generated near IR1 image can be transformed back to the near IR2B image by generator GA, and this image should be the same as that one. So we can define a cycle consistency loss of GA and GB, which is the L1 loss between the original image and the reconstructed image. And the total loss is a weighted sum of the adversarial loss and the cycle consistency loss. And lambda is just the weight for the cycle consistency loss. We actually tune this hyperparameter in our training process. We choose either lambda equals 1 or lambda equals 10. Now let's look at the detailed structure of the generator and discriminator. The generator consists of 3 different parts. The first part is an encoding network, consists of 3 convolutional layers. And the second part is a repeated application of several residual network blocks. We use either 6 or 9 resident blocks in our training. This is also another hyperparameter we tune. And the last part is a decoding network, which consists of 2 transpose convolutional networks with and 1 convolutional layer. And it should be noted that the final activation function of the generator is a 10H function, which gives output between -1 and 1. We can then easily transform this in the range between 0 and 1 as a final output. So the discriminator consists of 5 convolutional layers, and the input size of our image is 256 times 256 times 1. And the final output of this discriminator has a size of 30 times 30 times 1. So each pixel of the final output corresponds to a receptive field of 70 times 70 of the original image, and tells whether this patch is real or fake. Here are some results of our model. So the first row here is just some randomly selected near R1 images. And these 4 rows here are images generated by our CycleGAN model. And more precisely speaking, it's just images generated by the generator GA after training. So the last row are some results generated by neural style transfer. We can see here the near R1 images looks very blurry due to scattering, and it has very high background and low contrast. And let's first look at the results generated by neural style transfer. It seems that it has lower background and higher contrast. However, there are some artifacts. For example, let's see this picture. The bright region here actually corresponds to the spleen of an animal. It should be bright, but after neural style transfer, there are some dark spots here, which is very artificial. And compared to the neural style transfer model, the CycleGAN model works much better. And we can see the background is low, the contrast is largely improved. And also, the many key features of the original image is preserved. For example, this blood vessel here looks much more clear and sharper. To analyze the results more quantitatively, we calculate the Frechet inception distance, or FID, between the generated near R2B image and the real near R2B image. A lower FID means better image quality. And from this table here, we can see all the combination of these hyperparameters actually behaves roughly the same. And this hyperparameter, so with 6 resonance blocks and lambda equals 1, works a little bit better. And also, because this one has less parameters, which takes less training time, so we decided to use this as our final choice of hyperparameters. And actually, all these CycleGAN models outperformed the neural style transfer, which has a very high FID. It should be noted that our CycleGAN model is not yet perfect. For example, here are some failure cases. In these examples, it seems that after translation, part of the animal is totally missing. So, in my opinion, this is probably due to the low contrast of the original near R1 image. So, the model just recognized some part of the animal as background, and it will cause this kind of artificial effects. So there are still something we can do in the future. So here's what we're gonna do.
Some of our future work, including first, we can potentially collect more data for training, and second, we can probably do better on data pre-processing, like adjust the brightness and contrast of imaging before training, and that might help us like reducing the artifact that we've just talked about in the failure cases. And we can also try different architectures of generators and discriminators. Here, we used ResNet, and we could potentially use other like UNet-based generator and compare the performance with what we are using here. And last one is we can collect some paired data of near 1 and near 2B images and apply fully supervised image-to-image translation algorithms such as pixel to pixel, and this could potentially give better training performance.
So that's it for our project. Thank you.